Good afternoon, everyone. I'm Bailey Berry, a chemical engineering major from Jackson, Mississippi, and I work with Dr. Meenakshi Arora in the Drug Research and Engineering for Advanced Medicine, or DREAM Lab, in the College of Community Health Sciences in the Department of Translational Science and Medicine. And my project is entitled Stereocomplex Hydrogels for the Delivery of Anti-Inflammatory Agents in Dermal Applications. To begin, I'm going to give us a little bit of background so we can further understand the goal of this project. I want you to look at both of your hands and notice that they're mirror images of each other. But if you place them on top of each other, they're not the same, they're not identical. This means that your hands are chiral. And chirality is called the handedness of a molecule. And this occurs when the molecule is not, when its mirror image is not identical to itself. And molecules can come in the form of right-handed or left-handed molecules, RRS, or in this case, we'll use a more general form, D and L, with D being the right-handed and L being the left-handed, which is commonly used in biological applications. Now, chiral molecules, whenever they interact with each other and they have the same chirality, the interactions are normal. But when you have molecules that are right-handed and left-handed, they have special interactions between each other that are unique to chiral molecules. In fact, left-handed and right-handed particles can interact with each other and make these things into stereocomplexes. Stereocomplexes, which is in the graphic you see on the right, are these cage-like structures that are formed by the stereospecific van der Waals forces between the right-handed and the left-handed molecules. These have a large empty space in the center that can entrap particles or drugs that allow for it to have specific delivery. The way that we plan to take advantage of this is take advantage of the L amino acids in collagen, which is in our gel, and in our synthesized polymer, the D-lactic acid part or D-lactide part of our polymer, use those interactions to encapsulate our anti-inflammatory drug of choice, which is naringenin. Naringenin is an anti-inflammatory antioxidant that is commonly found in citrus fruits, specifically grapefruits. This cage-like structure will create a gel that will allow it to have advanced gel properties, advanced mechanical properties, and will be allowed to entrap the naringenin within it. So in summary, our goal of this project is to synthesize a stable gel with our synthesized D-lactide polymer and our L-porcine gel to encapsulate our model drug of naringenin. To begin this process, we have to synthesize our polymer. And our polymer is a chain of our lactide, which you see on the top left, and our polyethylene glycol, which you see on the top right. This is created through a ring opening mechanism, and it proceeds through a 24-hour reaction. Once we successfully synthesize our D-lactide polymer, we add that to a glass vial along with our gel. And in some trials, we add our naringenin that is dissolved in PEG 400 or polyethylene glycol 400. We also add 1 milliliter of water to this. This is stirred under heat for 1 hour and then is refrigerated at 4 degrees Celsius for 1 hour to allow the gel to set. In order to test the success of our creation of the gel, we want to look at two specific things: how stable this gel is and also how successful it is at releasing the trapped medicine or the trapped naringenin within it. So first, talking about gel stability, after we removed the gels from the refrigerator, we kept them at room temperature for 24 hours, then we inverted them. We determined that a stable gel was one that when inverted, it kept its shape and it stayed on the bottom of the glass vial. And one that was unstable was one that either fell, lost its shape, or was completely a liquid. If you look at the picture on the right, you see that the vial on the right is one that was stable. We flipped it over and it looked the exact same as it did when it was upright. However, the two vials on the left were considered unstable gels as they were too liquidy and too viscous to hold its own shape. These are some trials that we ran with various relationships of gel to polymer, and we found that all of our gels with concentrations of 3 or higher of our gel were stable, and we found various different trials with different relationships of gel to polymer to our naringenin. Lastly, we had to measure how our drug was released, and we did this by wrapping our gel in cheesecloth to kind of mimic what it would be like actually on the skin. We placed this cheesecloth and wrapped gel in PBS, which is phosphate buffered saline, just a neutral, safe solution to keep the gel stable as it's releasing the drug. And we removed them at various times, ranging from 30 minutes to 8 hours. Afterwards, these PBS solutions that had the released naringenin in it were analyzed using HPLC, and we measured the concentration of the drug in these solutions to measure how much drug was released from the gel over time. On our trial, we found that after 8 hours, 37% of the original amount of naringenin that was in the gel was released into the solution. So over 8 hours, 37% of the drug came out into solution. In the future, we plan to conduct rheometer studies to determine our mechanical properties of this gel, measuring things such as shear stress and shear rate, kind of determining how stable the gel is in a more quantitative way rather than just looking at it and flipping it over. Additionally, we want to perform cell viability and cellular uptake studies to measure how this would be like in an actual biological sense to hopefully move forward and hope that whenever we try this on cells that it's not damaging and it's successful. I'd now like to take any questions.
Hi, could you please go into a bit more detail on how you calculated the exact drug release percentages based on your measurements?
Oh, absolutely. So if you look at this, you see that on the bottom is our time, and then as it goes up, more percentage of the drug is released. So basically, whenever we took the gel out of the PBS solution, we put this into HPLC, which measured its concentration, and we multiplied that by its volume to figure out how much of the drug was in solution. So after 30 minutes, that was our first trial, we found that about 7% of the drug had been released. And so you keep on measuring that over time, the percentages add up, and over time, we figured out that 37% of the drug had been released.
So first of all, wonderful job. And I just wanted to ask why you would want to use this gel rather than something more like a skin cream?
That's a really good question. So many therapeutics, including the one that we're looking at, naringenin, suffers from poor solubility. And so not only does this give us an actual mechanism to put it on the skin without it washing off or anything, it also allows us to have controlled release. And we look at this, we see that in our specific gel that we use, that only 37% of the drug was released over time. And you can see that kind of difference as the graph goes up. You can see that it's more of a controlled release. It's not just all going in at once. So it provides a better way of delivering the drug rather than something like a normal cream.
How does cheesecloth emulate the structure of the skin?
It's more of a way to just see how the drug is coming out of the gel as it degrades. That's kind of how it's going to be delivered into the skin, is as those stereocomplexes break down, it releases the naringenin and it goes into the cells. So it's more of just kind of like a buffer between just sticking it in solution, making sure the gel is held together, rather than like an actual kind of study of it going into the cells. That's kind of what our future work is trying to look like.
So this research is trying to increase drug release, if I'm under the right understanding, but what is it in the clinical sense actually trying to enhance the treatment of? That's
a really good question. So as naringenin is an antioxidant and an anti-inflammatory, it will be treating things such as eczema or acne, more inflammatory conditions that are on the top of your skin.
Used D-lactide throughout this whole process, but did you do any trials using L-lactide?
Yes, that's a really good question. So we did do some trials with L-lactide, and we found that as compared to using D-lactide in the same ratios, that our D-lactide was actually made a more stable gel than our L-lactide, which suggests that these stereocomplexes are being created and are creating a more stable gel. But the L-lactide still forming gel suggests that the compound has gel-creating properties that are beyond its stereospecificity, but we do still see that the D-lactide gels were stronger, which suggests that the stereocomplexes are being made, it is trapped in the naringenin, and it is making the mechanical properties of the gel stronger.